In this video, we're going to discuss mass spring damper systems. The mass spring damper is a classical problem in mechanics that's the foundation for many problems in dynamics. One canonical example of a mass spring damper system is a suspension system that may be found, for example, in an automobile or a bicycle. If we wanted to design a suspension system, ultimately we want to make it so that the vehicle occupants have a comfortable ride over a wide range of road or trail conditions. To do that, we must first understand the dynamics so that we can see how the vehicle reacts to bumps, potholes, curbs, what have you. To do that, we first need to develop a model of the system and analyze it using the tools we have in our mathematics toolbox. For example, what we've learned in ordinary differential equations. In this video, we will set up a mass spring damper system, present simple models of springs and viscous dampers, apply Newton's laws to our system, and then derive the governing differential equation. Now, the suspension system on an automobile or a bicycle is rather complicated geometrically, but we will use a very simplified model. We'll use what's called a quarter car model, which you can think of as one wheel, which is traveling down the road, going over bumps as may be, and some factor of the car, maybe 1/4, depending on if it's the front or the back, and maybe plus or minus. That's represented by a mass, and the suspension spring is represented as a spring, and the shock absorber is represented as a viscous damper in this case. So the first thing we have to do is draw a free body diagram. And we will, whoops, where's my pen? To do that, we'll do a coordinate system independent at the moment. We'll just draw our mass. We know that we have a force due to gravity acting downward. We know that we have a force from the spring that is supporting the car. We'll draw it in the upward direction because physically that makes more sense to us. And there will also be a force due to the shock absorber, which will be a function of how fast the system is moving up and down, or how fast the mass is moving up and down. And we'll call that Fd. And again, we'll draw that upward, even though we'll see that that force will act both up and down over time. Now, ignoring the viscous damper for a second, let's look at a simple model of a spring. If we have a spring that's unloaded, meaning there's no force acting downward to compress it or acting upward to extend it, then we can call the natural length of this spring L0. Now let's say that we put our mass on top of the spring. The spring compresses, and it compresses enough so that the force of the spring acting upward exactly cancels the gravitational force downward. And so we'll put our mass on our spring, and we'll let it come to rest eventually. And we'll call this distance x0. And the reason for that will become clear, hopefully, in a minute. If we were to draw we've drawn a free body diagram, if we were to analyze our forces in our free body diagram here on the left, because the system is in equilibrium, we know that the sum of the forces equals ma. This always holds for Newton's, because it's Newton's law. If the system is in equilibrium, A is by definition 0, and so the sum of the forces has to equal 0. Again, ignoring the viscous damper for the time being, that means that Fs has to equal mg because they're of opposite sign. And our simple model of the spring for Fs is Fs equals k times the natural length of the spring minus the current length of the spring. So the natural length of the spring is longer than the current length of the spring because it's been compressed, so this number here is positive. The K constant is positive, so the force of the spring acting upward is positive. And so we can see that K times L naught minus X naught is equal to mg. Now, let's apply this spring force to our system here, and we'll need to define some coordinates that will make our calculations a little bit easier. So here's what we're going to do. We're going to say that when this system is at equilibrium on a, we'll call it a flat road, we'll say that there's some neutral position of the axis of the